I'm going to continue to study the algorithms today. I'm going to set the timer for 1 hour and then I'm going to decide whether or not I'm going to take a break or stop streaming. So I'm going to do Dijkstra, according to this, the pronunciation,
Dijkstra.
and Bellman Ford. I already watched a bunch of videos, but I still don't understand very well. I don't like the videos that much, because usually they explain just the algorithm first, then they go over the codes, and it's kind of confusing to me. So what I'm gonna do is just look at the code. I'm gonna try to reach a balance between not spending too much time on an algorithm, but also not going too fast, so I don't understand. So if feel like I spent a bunch of time and I still didn't got it, I'm just gonna move on to the next one because there's a lot of algorithms to study. I want to put some music for myself, I think. So this one, I remember I looked into last time. So the way that it works is that it initializes everything to infinity, like a very large number, the distance, and then sets the flag to false for checking which ones were visited or not. And then it just goes over all the nodes and updates the distances, which sometimes people call that relaxing. And then based on that, it finds the shortest path on a graph based on a source. This one I remember was kind of confusing to me because of this function here. So it receives the destination array of the distance array and the ones that were visited or not. So the destination is going to be infinity for all of them except the source, which is 0. So then it loops over them. This example here is just fixed, but if was a generic graph or for any graph, you just put the length of the thing here, I think. So if it wasn't visited, if the node wasn't visited and the distance is smaller than minimum or equal to the minimum distance, which is the maximum here, then it updates the distance. I think that the thing that was confusing to me last time, which I'm still confused about, is why, because here is going to be 0 and there's no distinction, so this is going to become 0. So I don't understand how. It seems that is not the correct algorithm. I don't remember where I got this from. Maybe it was from Geeks for Geeks. Because it wouldn't make sense for this to be 0, like regardless of what happens, and it's gonna be because of this thing here. It's gonna be not gonna be 0. It's gonna be the index of the source. This is returning the index. Then it sets to true. And then it loops over the things again. So maybe this part will clarify that. So, so if this is false, then obviously it's gonna be true. And graph mi. And if the current node has a neighbor, I think that's what this does, because it's a nested list. So like the first list is the list of the nodes and the other list is the neighbors of the nodes. So the edges, I assume that's how this works here, like the way that they did it, this one, because the graph is an adjacency matrix. So this checks to see if the current nodes that is checking based on this thing here. Oh, I guess I understand now. It's because it's gonna be a loop. Yeah, I was tripping, I think. So it makes sense because this is gonna be it's gonna be the source in the first because it's gonna be 0 and the other is gonna be infinity, so it returns the source. And then it loops over the neighbors of the nodes again. And then it checks to see So it's just pretty much just going over each node and their neighbors and updating the distance. It's not that hard actually to understand. This was just like confusing because I didn't realize that there was a loop here. But I think last time I also thought about this, that like it does make sense if you call the function more than one time, but it doesn't if you just once, obviously, because then it's always going to be the nodes. M is always going to be the source node, the index of the source node. Okay, so let's see here. So the distance is checking for the value if it's different than the maximum value. Because if it is this value, then it means that the distance wasn't updated for that node, which is based on this one here. Hmm. The distance of the current nodes plus the value of the neighbor is smaller than the distance of the index of the node of on this index. So I guess that this one keeps track of the distance from the source node up until the current node that is checking here. So it's the absolute distance from the node that is started to the current node. And then it checks to see if that distance is greater than the one that you will have by adding the next node on the path. I think that's what this is doing here. It's checking so this thing, obviously based on the name, is gonna find the minimum distance based on all the distances and based on which ones are visited or not. So you're keeping track of which ones are visited and the distance between them. But I'm not really sure. Like, because this is the overall distance. But I think that this is gonna be the max each time that it calls here. So it's always gonna be the max. It's just checking the absolute minimum distance. I guess it's confusing because of the way that is declared here. Because you have to remember this from the source, so that's why it's just one, I think, array here. Like this is not a matrix, it's just an array of 6 integers. And each one represents one node. And then each node has its neighbors, which is the adjacency matrix of the graph. The source starts with the 0. So like this is going to be the index of the source in the beginning. So it starts at the source, and then it updates the source to true because it was visited. I guess it doesn't like the order of the nodes already embedded into the adjacency matrix. So that's the thing that I was thinking about. Like it doesn't matter that is going over just one by one here and here. It's just going over all of them, but maybe it could be optimized. Like because if you checked for this outside of the loop, but maybe not. Because the thing that doesn't make sense here to me, I'm not really sure if it would be worth it to optimize, or maybe it would be You just make everything more complicated, or maybe it's not possible. But I think that doesn't make sense. Just why loop over all of them all the time, like inside of here? Because you're not gonna, it doesn't matter the ones that are not false because they were already visited. So you would save time. But I guess, but this is the thing that is kind of confusing to me because it is what I'm thinking about, I think. Because it's not that you have to loop over again because you're looping over the neighbors like each time. So you have to loop over. Like you're just looping, you're doing the main loop to see the main nodes of the graph. So that doesn't make a lot of sense to me. It would make more sense to somehow check to see if they were visited before. But then like the only way you could do that is if you keep a hash map. So that's what I was thinking about, like create a cache and then store the values. I think it's possible to optimize this. This is why it's kind of confusing to me. But I'm not gonna. I don't think I'm gonna bother with this stuff. And the main thing that I'm trying to achieve here is to, which last time I talked about this as well, that I don't like is that, and there's this very good book that I recommend. It's probably one of the best books I've read. Um, 7 Habits of Highly Effective People. Okay, the name of the book is Seven Habits of Highly Effective People. I don't want to show. I mean, maybe it doesn't matter if I cover the thing on Amazon. And it's by Stephen R. Covey. But whatever, I'm not gonna show the thing. But pretty much one of the principles that he talks about in the book is that you should begin with the end in mind. And I think that's the main point of disagreement I have with the current systems, but it goes very uh, deep. So obviously there's like several different things, different reasons why it is like it is today. But I'm trying to move as close as possible, as much as I can to this kind of thinking. So like I'm studying these algorithms to based on the stuff that I want to do. And I think that's the best approach. I don't want to spend a bunch of energy solving problems that are not related to like actually building systems that improve society. So yeah, but this is the best that I could find so far, best method, and I'm trying to work towards building something that is a lot more effective. So like you begin with the stuff that you actually want to do. Let's say you're interested in biology or economics or logistics or anything like that, or networks. And then based on that topic, you search what are the most useful and effective algorithms on that domain. And then you study those algorithms to try to abstract the first principles thinking from them. I think that's the most effective way. So the reason why I'm saying this is that like even though I think that this can be optimized, I think it's not worth it to spend a bunch of energy just trying uh, to do this. Like it's better to just I think because the thing that I'm thinking about doing is to write these algorithms down a bunch of times until I kind of memorize of like the how to build it. But I'm just doing this as to increase the strength of my baseline of memory. So I don't have to, like when I face a problem, I can just start from the initial point of already having the template. And then if I want, I can optimize later. But I don't think it's worth it to spend a bunch of time. And it goes back to the thing that I was saying of trying to find the balance between not going too fast and not going too slow. So I don't want to spend a bunch of time, even if I don't understand the algorithms. I think it's enough to just get the general picture, and then from that point, like create a funnel of hierarchy based on the stuff that you're actually gonna do. So yeah. So here, if my thinking is correct, I think that this is what's happening here is like looping over all of the nodes, each iteration. But maybe it's the neighbors, like he's looping over the neighbors, but that wouldn't make a lot of sense because this is only one array, is not a matrix. So it has to be only one dimension. But yeah, maybe it is looping over the neighbors, but I think it isn't. I think it is looping. It would make more sense that it loops over the main nodes. So the first dimension of this adjacency matrix is related to the nodes. The second is related to the neighbors of the main nodes. And it would make more sense that this is related to the first one because it's the main nodes. So I think that each time is just looping over, that is looping over them is checking to see if what is the absolute minimum distance based on this check here and based on the ones that were visited. And this distance is the value calculated from the source, which is the one that you pass here. And then in the beginning, this one is 0. The distance from the source to the source is 0, obviously. And I think that with each iteration here is just adding like the value on the absolute distance from the source to that node is gonna be equal to this thing here, which just grabs the value of the node itself, which is the weight of the node, I think, and adds to the current distance, or yeah, to the current minimum distance, the minimum absolute distance. That's what's happening. So I think I understand now how it works. And in my mind, it's possible to optimize this one by creating a cache and then removing or putting this condition outside of the loop, like making the loop dependent on the, or maybe you don't even need a loop. Maybe you can do it just with the cache. I'm not really sure though. Maybe, yeah. Am I thinking correctly about this? Because the main thing that it looks weird to me here is that is looping over all of them each time, and it seems unnecessary because of this condition here. Because you're already tracking which ones were visited already, so it wouldn't make sense to loop over all of them. If you maybe instead of doing the loop, you could just create a cache, like a hash map here, and then you pass the hash map instead. Then the hash map, but maybe, or you filter. You filter this, but then it would be the same thing probably. So I'm not really sure. Maybe there's a way to check and then only pass the ones that are true and loop over the true ones to see if the distance is smaller than the minimum. Oh, but actually, maybe it's looping over all of them because because of this value. But then again, you can cache the value. I think that this value is going to be max each time. So I'm gonna move on, but it's no. I feel like there might be a way to do this in a more efficient way, but whatever. I think I got the points. Probably not gonna use this one. I think I'm gonna do Bellman Ford, and then maybe I'll search for. I could do the stuff that I was just talking about, but the thing that I'm trying to achieve is to create. The reason why I'm studying compilers and trying to build a graph is so that I can extract the patterns, fundamental patterns. Because initially, the reason why I'm doing this list here and study this is because the main question I always have whenever learning something is what are the first principles and what are the fundamentals of that thing? Because those are the things that are going to be happening 80% of the time, because it's probably going to follow the Pareto distribution. The thing is related to energy and Occam's razor based on the pattern of gravity. So, yeah. So the question is like, how can I find what are the fundamental patterns on C so I can memorize them and I don't have to think about them, and then I can focus on the complexity of and nuance of the problems themselves, which I think it is the paradigm of machine learning as well. Like it's just based on gravitational force and density because that creates a probability network, which is the Bayesian thinking, that generates gravitational force and then it becomes this loop. So like what you're always trying to do is reduce variance into relative mass because that increases the probability that the system you're building is going to be reliable. So I think that it might be better. Encryption, I want to uh, study a lot more because it's related to crypto, and I think that's how probably the key to alignment is to create a mathematical framework around encryption that allows nodes in the network to converge towards a relative equilibrium that is sustainable, I think. So obviously encryption is very important to that for that reason. So I'm probably going to spend a bunch of time studying these ones. But the other ones maybe is not very useful. So maybe I should like remove them or go faster over them. I'm gonna look into the Belmont 4 one, then I think about this. I think I'm gonna maybe I'll just go over the other ones very fast to understand how they work, but then I remove a bunch of them and then just focus all my time on the ones that I think are gonna be relevant to the stuff that I'm interested in. Oh, there's also the other algorithms that are important for me is obviously the ones related to a compilation process. So probably anything that is string related and the register graph coloring algorithm register. I watched a bunch of videos about this one, but I still the videos are not very good. So and then maybe trees as well, because trees, I think that the reason why trees are so useful is because it's related to the flow of time, because the flow of time is going to be a hierarchy and it's always relative, and so that the optimization for computation is always going to be converging towards the tree data structure in some way, because that's how the big O notation evolves, I think, over time. So the memory is correlated with the speed, and the correlation is always going to be towards either a tree. I think that tree is just a simplification because it's going to be more like a curve or a wave function. So a Gaussian from Pareto to Gaussian and from Gaussian to Pareto is going to create a frequency of waves that change geometry. So I think Bellman-Ford is very similar to Dijkstra. It's just an algorithm to find the shortest path. I think the main difference is that Bellman-Ford works with negative weights, but I'm not really sure. So let's see here. So I think that's the same thing here, is initializing everything to infinity based on this adjacency matrix here. Not sure what n is for. And is adding edges. Let's so it adds a source destination. So it's just mapping the adjacency matrix, which is this one, with this initial value, which is probably going to be a random value because it doesn't initialize with anything here. And then increases. It's kind of weird that here's 8, not really sure about that. Because it should be 5 based on the numbers. Yeah, but whatever. Maybe we should ask ChatGPT about this thing here. Because it's probably capping the number of neighbors for each one to 5. But then the first one doesn't have a index because it's going to be arbitrary. So I think that's what makes sense to me. Let's see the destination. Yeah, but it doesn't make sense to. So both I and j is going to be 5, the maximum. So I don't understand the 8 here. Oh, this one. So this one you have to put. So character in the 2 arrows on C++ indicate the flow of the string. Character counts is character out, and sing is character in. This is just saying that whatever it creates an input when you run the program, and whatever you type is gonna be this value here. It's gonna go to this variable. No, this is gonna be out actually. So uh, this one is the one that is in. So I think that's when you it's gonna output this as the like command on the terminal when you run the program, and then when you put the number, it's gonna go to these values here. I think it becomes I and j and costs. Yeah, so I remember that I ran this at some points. So you input three numbers, and then the first one's gonna be I, the other one's gonna be j, the other one's gonna be cost. I gotta be honest, I don't like that much this way. Maybe I'll try to find another one, another implementation. Let me ask ChatGPT after. Let me see if I can understand here. Then ask ChatGPT to create another one. Just looping 5 times from 0, 0, and costs infinity. Initialize all the costs to infinity. And the minimum is a very high number. If minimum is greater than a cost. So it's just creating this value to keep cache the minimum value over all of them. And then it checks to see if the current node has value. Okay, so this is a struct. This is an array of structs. So each node is gonna have these values here. So this creates an array, as far as I understand, an array of 5 nodes, which are these structs here. And then here is accessing each one. So the node is gonna be the node on the graph, obviously. Just checking to see if the node has the value, or if the value is equal to 0. Because it initialized everything to 0 in the beginning. This is like similar to the other one. I think that but the difference is that the other one tracks based on true and false, which ones are visited. And this tracks with the 0. So the value is 0, that means the node wasn't visited yet. So if it wasn't visited and the cost of the node is smaller than the minimum, which is the absolute here, then the minimum becomes the current cost. So this is just gonna find the current minimum. This loop is here. Then loops again. I'm not really sure why I do this stuff here. I guess it's so this one is greater than. So if it's checking to see if the minimum, the node that has the minimum cost was visited. I think that's what's happening. And if it was, then it breaks. If not, it just skips. I don't get this very much. I think it breaks. Yeah, no, I'm not really sure. But I think it's just gonna break this loop here. But maybe it breaks the. It wouldn't make sense to break that too. So break just stops the loop, and continue just skips the iteration. So I don't understand very well why you do this. Seems like unnecessary. Or whatever. Oh, it's because of this thing here. Yeah, but I don't like this, to be honest, the way that this is done. It's very confusing. Like this is just checking to see what I is gonna be, what is the index of the node that has the minimum value. That's what this is doing, and then it puts this on this temporary variable here. I think it would be maybe like it would be more like better to it would be easier to understand if it was like here, I think. Oh, well, whatever. So I'm gonna assume that this is what's happening here. So it's checking the current minimum and then going over all the neighbors of the current minimum. So if the current neighbor plus the cost of the current one is lower than the cost of the current node, which is a similar condition to the Dijkstra, is checking to see if the value of the current minimum value plus the value of the neighbor is smaller than the value of the cost of going to the neighbor, I think. And if it is, then it updates the values. That's very confusing. And then here, ATM value equals to 1. So this marks that the node was visited. So it's using the value to check to see if the nodes are visited or not. If they were, then is 1. Not then. And then it's gonna go over all of them on this loop here. So I think I kind of understand, but I don't like very much the way that they wrote this. It seems more confusing than it has to be. But maybe, yeah, maybe not. So I think I'm just gonna move on to the next one. So let's see. I think I'm gonna go. Some of them I marked as that I went or that I got the code, but I got the project. A lot of them are a lot of these situations are when for the encryption ones, because a lot of the algorithms are not very simple. It's just not one function. It's like entire project, or it's was very hard to find a single function like separated. So I decided to get all the projects their libraries. So those ones are gonna take a lot more time, I think, to study. So I think that's the register allocation is one of this. So for register allocation, what they do, I don't understand very well the nuances of it, but they create a graph and then it colors the graph based on like I think what registers are used or something like that. Maybe I'm gonna ask ChatGPT and then I'm gonna search for a little bit. Data flow analysis phase of compilation. Interference graph is constructed. In this graph, nodes represent variables. An edge between two nodes indicates that their corresponding variables cannot be assigned to the same register because they are live simultaneously. In their use are defined in overlapping program segments. So a register is just a faster memory than RAM. So dynamic RAM or random access memory is just a collection of registers, and a register which maps address with data. And both addresses and data are just collections of zeros and ones on the hardware. So like the transistors are used to indicate on the hardware where the bits are gonna flow next. And it's based on the frequency of the clock cycle of the computer, which changes the resistances on the wires. So based on that, you have like the logic of the computer. And then the data, I think that's probably the distinction between, actually I'm not really sure about this, I have to think more about it. But the distinction between algorithms and data, it might be that the data is just related to the zeros and ones you want to encode into a piece of hardware, like a RAM or register or stuff like that. And a program is the bits that are related to the coordination between multiple different parts of the hardware. It might be the distinction there. But I'm not true. I don't think that's like it's not that. I think actually it's gonna be like one of those, like everything is gonna be a multifractal distinction. So it's gonna be a gradient, and then over that gradient, it's gonna converge towards infinite potential. And then at the moment that it converges, it breaks down. Like it becomes a paradox. That's how reality works, I think. So like what defines the distinction is just an illusion, because it's like, yeah, is the projection of the computation of the current state of the present moment, which is the definition of space-time. So all distinctions are relative, and they're just a frequency of the frequency of computation that creates geometry. So you're always going to have relative polarities that are in interaction with each other over a frequency, and that creates geometry. And the boundaries between things are always going to be multifractal. And I think that the imagination is a lower density space that represents the abstract notion of this thing. It's just a funnel of information. From the abstraction, you have geometry, because abstraction is when you decrease the density of matter. So instead of like, it's kind of like purifying or simplifying the boundaries between things. And that's what abstraction does, is like a simplification of the boundaries. So geometrical shapes like triangles and other stuff like this is just what happens when you analyze the multifractal space of space-time and you abstract away the essence of the thing, like on a lower resolution way. So it's going to be the same thing, I think, on the distinction between data structures and algorithms. So I think that's going to depend on the circumstance, how exactly you put the boundary. But it's probably related to this distinction between coordination of like the bits that are used to coordinate different parts of the hardware and the bits that are used to dictate the pixels on the screen. The goal is to color the nodes of the interference graph with a limited number of colors registers such that no two adjacent nodes connected by an edge have the same color. If this can be achieved, it means that that variables represented by the colored nodes can be assigned to registers without interference. Graph coloring algorithms. Graph coloring algorithms such as the famous greedy coloring algorithm or more sophisticated algorithms like Shettling's algorithm are employed to find a valid coloring for the interference graph. Spilling. If the interference graph cannot be colored with the available number of registers, a spill may occur. Spilling involves saving a variable's value to memory, spilling it onto the stack when it's not in a register. This allows freeing up a register for another variable. Graph coloring techniques help in optimizing register allocation by minimizing spills and efficiently utilizing the available registers. Efficient. So I think that the pattern of a stack is kind of like a same thing as a wave function. It's just like up and down. So like you have wave functions creating trees because that's the nature of perception. So like it's a funnel of information. Another thing that I was just thinking uh, the other day, or maybe today or yesterday, is that I was thinking about like reducing like programming languages into mathematical equations. And I thought about like what is the difference between network protocols and algorithms, because everything is just a programming language at the end of the day. And I think that the main difference that I just realized is that the network protocol is going to be synchronizing different hardware architectures. So network protocols are the difference, like the generalization of hardware architectures. And then hardware architectures create the assembly instructions, so like the standards. So the complexity of the network protocol is going to be directly correlated with the variance of the standards that are created for the assembly instructions, I think. I'm not really sure. And that's going to be related with the deterministic finite automata. So that are non-deterministic finite automata that creates the language structure. So let me spend some time thinking. I think graph, this one's probably worth it to study now. So this one, I'm probably not gonna do the other ones, to be honest. Maybe I should do these ones very fast. Yeah, I think I'm gonna do these ones very fast because they're easy, I think. So, and then I'll do this one. Yeah, so the main thing that I want to do is create a graph out of a compilation process. So I have to, and obviously the encryptions are gonna matter. Encryption network protocol. Maybe I should ask ChatGPT. I know that I don't know, but I think that Fourier transform is used on, which is also another one, also compression as well. It's both encryption, compression. These ones are very good as well. This stuff that I'm interested on right now. It's like encryption, compression. What was the one that I just saw? And Fourier transform. Just Fourier transform and like the changing the nature of information. I don't know how to say this, like, but like from video to audio and that kind of thing. I know there's some graph algorithms, but I'm not really sure if that is the graph algorithms that are implemented in relationship to network protocols. I think is just for calculating the optimal way to send the bits across the wires. They're not related to like the fundamentals of encoding and decoding the information. So I think compression is more important. Compression and encryption probably, which are ones that are more important. And shortest path, I think state routing and distance vector routing. Flow control. It's also something that It's very intuitive once you think about it, but it's not natural to think about it this way because I'm not really sure why, but like sending bits is actually the same. It's very similar to sending water to through structures because you're just sending electrons. So, and the thing that I think is not very clear about this is that, and I remember seeing not that long ago is that like we have the picture of your mind where you're sending the electrons, but that's not precisely what's happening. What happens is just like it's more like a wave, I think. So I'm not 100% sure if what you're doing is like sending one electron because of the whole thing about the uncertainty principle. We're not sure if it's a particle or a wave, but it's probably the true because I think that's gonna be a paradox because that's the nature of reality. Like everything's gonna be this pattern, I think. So like the uncertainty principle is just paradox because paradox is the boundaries of any system because the nature of space-time is just a reflection of the computation of the network. So it's like a hologram. It's a projection of the the present that creates the illusion of the past and future because past and future are born simultaneously through the present. So it's just a computational frequency, I think. Like the what defines space-time is the irreducibility of the computation of a network in relationship to a reference frame. And that's why the boundary between P and NP exists, I think. So like they are the same thing at the end of the day, but at the same time they are not because what defines the structure of space-time is going to be the gravitational frequency that creates the distinction between P and NP, which is going to be a multifractal boundary, I think, which is geometry. So let me, I'm going to do the simple ones. So binary search. I'm going to do the simple ones then I think I'm going to do this one, but then I'm going to focus more probably. I think encryption is going to be the most important for me. And I think the other ones I'm going to just watch videos off string and I'm not going to dive deep into them because they don't matter too much to me. So fast food and transform also I think matters a lot. And so compression, so I'm going to write uh, probably encryption is the most important, then compression. And then the thing is I'm not really sure like changing domains. Like how can I say that? Like the difference between how the structure of information becomes something. Because it's all like it's all relative, obviously. So everything is going to be the same at the end of the day, and the separation between things is the stuff that I was talking about before. Just like the only reason why you have the concept of the difference between things is because of the computational frequency of the network that creates space-time, which I think is the electromagnetic field. That's why I have the complex plane is imagination, which is a or imagination or abstraction, which I think is the same thing, and it's just a lower density uh, version of space-time. So like they are interconnected, and the connection of them is their paradox, which is a singularity, which is the nature of the present. So that creates the illusion of past and future, but they are the same thing, I think. So like the funnel of information of gravity is the illusion that things are happening. So like the future is going to the past because that's what computation is a symbolic representation of a network. So if that's true, then that means that there is no distinction between anything. Like what defines the distinction itself is the frequency of computation, and that creates the geometry. So the difference between any concept, the audio or video or text is just gonna be like arbitrary, and it's gonna be probably a multifractal because at the boundary is like the limitation of the computation of the nature of space-time right now. So the paradox is gonna be like the encapsulation of the approximation of the future, let's say, because what defines the paradox is the relative boundaries between things that defines the geometry of space-time. So I think that fast Fourier transform is related to that because it's related to the complex plane. Because I think that when you bridge the gap, what you're doing is just trying to approximate the complex plane. I think, but I'm not 100% sure about this. Like I view it as the complex plane becoming space-time, and that happens through the complex plane. And like the boundary is from the complex plane to space-time, and that creates the paradox. So quantum mechanics and this like fast Fourier transform is like this process of approximating or creating geometry based on the uncertainty principle, I think. The domain related to converting sound to video, video to text, and similar tasks is generally associated with multimedia processing, information retrieval. Evolve. Yeah, but I'm not 100% sure, obviously. So I want to understand more, like how does that work? How is information encoded into sounds and video? Fast Fourier transform is indeed related to multimedia processing, especially in the context of audio and signal processing. The FFT is an algorithm that efficiently computes the discrete Fourier transform, which is a mathematical transformation commonly used in data analysis, in the analysis of signals, including audio and image data. It's a mathematical operation that transforms a signal from its time or spatial domain into its frequency domain. Time or spatial domain into its frequency domain. The discrete Fourier transform is a specific form of the Fourier transform designed for discrete sample data. Standard DFT has a time complexity of O1 square, or O1 to the power of 2, where n is the number of data points. The FFT reduces this time complexity to this, making it much faster for large data sets. The basic idea behind FFT is to divide the DFT computation to smaller subproblems. The Cooley-Turkey algorithm is one of the most common algorithms implementing the FFT. It involves recursively breaking down the DFT into smaller DFTs until the base case is reached. I remember I spent a bunch of time studying this stuff, but I still didn't understand very well when I was studying the Ethereum network. If I remember correctly, on the Ethereum network, they use FFT and extended Euclidean algorithm for some cryptography, I think, or somewhere there. I don't remember exactly where. I think it was part of the EVM itself that these algorithms are used. And I was trying to understand, but I watched a couple of videos as well. So I think that generally the way that it's gonna work is that you're gonna have polynomials, and then you transform the polynomials into lists or arrays that contain the indexes of the x. So like x to the power of 2, x to the power of 3, and so on. And then you convert that into lists, and then you convert the numbers from the real plane to the complex plane or something like that. And then based on that, you do this transition, but I don't remember really well. I think I'm gonna spend more time studying this one. So I probably this one first because I'm familiar. So I will do this ones here, then this one. Then after I do this, I'm going to after these ones and this one, then I do the fast foreign transform. So I'm gonna put here. These ones I'm gonna do now, but I just so I remember this one. This one. The other ones I'm just gonna watch videos, I think. And then I will do these other ones here. The full category. I have to I didn't understand this one very well. I think that this Huffman coding compression works by because everything you pass through the wires is going to be strings, and then each word is going to be a byte, I think. Just a binary representation, which is going to be based on a standard that gets created, which is usually UTF-8 or ASCII, or that one, whatever, however you say that. So that's going to create a standard that dictates that each character is equivalent to a number, so that number becomes a binary representation, and then you pass the binary representation through the wires over some protocols that like you have to pass frames as well. Frames and a bunch of other information to specify the path of the network for the computers to, and then you have the DNS, which is the domain name service, which is going to be equivalent to the IP address. And then based on those information, and the MAC address, which is the address of the device itself, and then based on those informations, you're gonna pass the headers. That's the purpose. That's the purpose of the header. It contains all this information to send the bit to the correct place. And the cryptography part, and I still not, I don't understand very well. But basically, the idea of this one is instead of using always 8 bytes for each word, it creates a 3 data structure, and that allows it to compress the amount of bytes you use based on how frequently the words are going to be used. But I didn't understand very well like how does that work. So probably puts here the compression ones I don't have a. So probably what I'm going to do after I watch all these videos about all of them is just create another category here and then remove all of these other ones and just put compression. This probably makes more sense. That's what I'm gonna do. So I'll be right back. When I'm back, I'm going to let me finish reading this stuff. Then when I'm back, I'm gonna study these ones. Oh, FFT is also used for compression. Image processing FFT is used for filtering operations in the frequency domain. It enables operations like blurring, sharpening, and edge detection. FFT is employed in image compression. Algorithms transforming an image into the frequency domain allows for efficient representation and compression of the image data. Signal analysis FFT is a fundamental tool in the analysis of various signals, including biomedical signals, blah, blah, blah. Frequency modulation and demodulation. Communication systems, FFT is used for tasks like modulation and demodulation, helping to encode and decode information. Scientific simulation FFT is extensive. So, like, the thing that I don't understand very well is like this, like, why is the assumption or like is assumed? Not really sure if it is really an assumption, but like the notion that it transforms spatial data into frequency. I'm not really sure if it's vice versa. I don't understand very well what that actually means. So I think what it means is that there's this relationship between these things based on the multifractal pattern of space-time. So like what the fast Fourier transform is doing is converging the relative region of space-time into its multifractal abstract representation, which encapsulates the lower density, which is imagination, which has the higher potential in relationship to the complexity of the current space-time. because I think everything is happening simultaneously. So, and the notion that is happening in a linear way is just a human notion, which is the reduction of the infinite potential based on a computational reference frame, which is the symbolic representation that we create, or that space-time creates based on the relationship between the electromagnetic field, which I think is going to be related to black holes, because black holes are going to be the boundary. So the event horizon is going to be the boundary of the computation, which is going to create geometry. So I think that fast Fourier transform is directly correlated with this process of crossing the bridge, but I'm not really sure like if that makes sense or not. I think I want to clarify that more. Be right back. So let's do the binary search. So binary search, the way that binary search works is just by you get a range, so it has to be sorted. As far as I understand, could be wrong, but you get a sorted range, and then you divide the range in half, and then you compare based on whatever target you have. So you're just getting a range and then dividing that range in half, and then based on whatever value of the target you have, you compare with the range. So if the value is smaller, then you go to the left side of the range. If the value is bigger, you go to the right side, and then you keep dividing until you find the number. So I think it's pretty simple. I was just looping over all of them and then running binary search for all of them. So it puts past the target the size of the array, I think. Yeah, size of, and then the array. So left is gonna be 0, obviously. The right, so because it's the index. The right is the size of the array. Middle is 0. Then the middle is gonna be Left plus right minus left divided by 2. I don't understand very well why do the left here. I add this left to the middle. And then it narrows the range based on the value. So if it's bigger or smaller. And if it isn't, then it founds. Also return true here and then return false here. The only thing that is kind of confusing me is the why the left, why add the left index here, not just get the middle. So if the value is bigger than the current value on the, which is going to be the middle initially because it's 0, then it goes to 1 to the right of the value because obviously it isn't the value itself, the middle itself, because it's smaller, because the value is bigger, not equal. So it updates. So I'm not really sure if it's necessary to do this part here. I think that's probably works like this. Yeah, I don't see. Oh, maybe not because it's making the right equal to that. So it makes the left equal to middle plus 1. I'm not 100% sure. So I think it's because of the way that he did the loop and the calculation. But yeah, now that I think about it, it doesn't make a lot of sense. Maybe this is not right. Because it's always going to be this. But it actually is, it does change the value here. So this is going to be the previous middle. Which was half. This would be 0 then. No, half. Let's say 0 and 10. Let's say n is 10. This would be 5. So this is equal to 5. 0. 0. Oh, because it is smaller. I think that the left is in case you have but maybe not. So like if it was 0 and 10, then this would be 5 in the beginning. So the right would be 5, and then here would be 2.5. But actually, it's gonna be probably true. But the left is still 0, so. I'm not really sure if it makes sense, sure. That's probably right, but I don't remember where I got this from. I think it was probably from a website, so side chance that is right. It's just the calculation that is confusing. It's, it should be integer division, so it's gonna be true. If we divide 5 by 2 instead of 2.5, it's gonna be true. But the left's gonna continue to be 0. So you would search for for the middle, which is 5, then we'll go to 2, I think. I don't understand why increase left here. Let's say the value is bigger. And becomes 6. Yeah, this doesn't make sense to me. Because if it's 0 from 0 to 10, and it's bigger in the first, so the middle is going to be 5. Say it's bigger than the value. So left is going to be 6. So here would be 6. The right is still 10. So 10 for... Actually, it does work. It's just because you have to... Because the way it's going to update here, you're going to have uh, the baseline to add. Hey, what's up? Salve. I'm gonna move on to the next one because like it doesn't matter that much. Um, I probably like because like I said before, I was gonna because initially the reason why I wanted to do the raps is just so I get more used to writing stuff with C++. It's more like, but I think it's probably not gonna be very good. So still think I'm going to do it for some of them, like breadth first search and depth first search. Like just write down the algorithm a bunch of times until I memorize. But I think that's not going to be very helpful because it goes back to the thing where I'm trying to more like find the fundamental patterns of the language. And I think also I'm going to read these books here now. So I think that probably for that it's going to be better to try to search for books, maybe use ChatGPT and then try to find videos as well. And then for the algorithms, I should focus more on the stuff that I said here, like encryption, compression, and these other ones. Like study the projects and then just do the wraps for a couple of them, like a couple of the graph ones, and maybe actually these ones are probably worth it to do the wraps. So I'm probably gonna do for these ones, especially linked lists that I like find it very difficult, and I think linked lists is probably a good way to train pointers as well. So I have to go back and review the Kenneth Rick book for pointers to train. So I'm probably gonna do that as well, and then write down the exercises or the examples he gives for pointers, and then just do the wraps for the pointers. That's probably a lot better than doing the wraps for these algorithms here. Like these ones, I think I'm still gonna do it. The implementation of the queue, the heap, and the heap is just a binary tree as far as I understand. And then you have the max and min heap. The max heap is gonna be when you have the highest value of the nodes at the root of the tree, and the min heap is gonna be when the minimum value is at the root. But they're both trees. So let me. Quick sort was very difficult to, not very difficult, but it is kind of confusing to understand. Not sure if I'm gonna try to. Basically, from the videos I've watched, you get one value in the beginning. Usually, it's gonna be the last item of the array, and then you go over the array and you compare with that value, and you use that value to create sub-arrays from that value. And you do that by comparing the value. So if the value is smaller, then you swap, smaller than the current one. If it isn't, you don't swap. And that creates two sub-arrays based on the initial array based on the initial value you got. So for example, let's say you have an array that goes from, like it wouldn't be sorted obviously in the beginning, but the highest value is 10, the lowest value is 0, and you get the 7, or yeah, 7, you get the 7 as the initial value. And you would compare all the values inside of the array. With 7, if the value is smaller, then you swap. You compare two different values. If they are smaller than 7, you swap. So basically, you're just trying to achieve like choose subarrays that are, one has all values are lower than 7, and the other all values are greater than 7. And then you keep doing that stuff until you sort everything. So I think it's pretty much kind of like that, but it's kind of confusing to understand. So the partition is the parts of splitting the main array into subarrays. And the other one here, like the recursion, is to do this like a bunch of times. So for each subarray, you're gonna do this division again, and that's why you do the recursion here. So they start 0, the end is the last thing. The arrays here. So if the start is bigger or equal to the end, you return. And this means that it was like you went through all of them. So here is just decreasing one by one the end, and here increasing the starts. And this, so it's kind of like breaking down the things, because this is gonna be like the partition. So like this returns the element that is at the index that broke down the two main arrays based on the initial value. So it's just calling the function recursively from the left and to the right, which are the sub arrays that the main thing created. So I'm not really sure if that's clear or not, but I think I understand now how it works. Yeah, I'm gonna move on to the next one. Merge. So merge sorts, as far as I understand now, you're just dividing the main array into smaller, like into half, and then you do that until you only get to one element, and then you sort them as you backtrack to the beginning. So like you get to the base, which is just one element, and then you compare that element with the other one, and then like when it's going back up again, you sort sort each one. I think that's how it works, and it probably works with recursion. Probably there is a loop implementation as well. This is the same thing, but so same thing as the other one. It has a base case and then calls recursively based on the middle. So apparently this is the correct way there, because on the binary search one, because these ones are using like this as well. It's kind of confusing, but I think the reason why it sums here instead of just getting the middle is because the way you update the values of the middle. So it's either going to be on the beginning or the end, and so you have to add the baseline, which is the left value, in order to get the middle of the new array. I think that's why you have to sum there. Yeah, so one call is from the beginning to the middle, the other is from the middle to the end. So this part here, which is very confusing to understand when it comes to recursion. So like this stuff here is this call is gonna create like all the arrays that are from the middle to the left. It's gonna create smaller, smaller until we get to the base case, which is when the beginning is equal to the end, or equal or bigger. Then from that point, it's gonna go back and one. It's gonna go back one time from the last execution, which is when it hits this, and then it's gonna continue executing from that point, which means that it's gonna call this one. So it goes all the way to the left, then it goes back one, and then starts going to the right. And then it does that. That's gonna generate a tree with all the different arrays, I think. When it hits the base case, like the base case from the right, then it calls the merge here, which is just probably gonna compare the two different ones, the remaining elements. Recursion is very confusing. So it creates temporary arrays, show the data. I don't want to spend all like the time to looking through the nuance or like verify that it's correct, the variables here. But I think I understand the logic. So like this part is just gonna compare to see which value is bigger or smaller, and then it's gonna reconstruct the arrays based on that. So like on the sorted way, just getting the smallest array possible, then it calls this function at the end. Once you reach the bottom of both left and right, and then you're gonna have the minimum array from left and right. Then from that point, you call this function is gonna compare the values. It's just sending one array at the end, which is gonna be the last array that you have. So like when on the backtracking, I think is going to sort the elements. It's hard to understand recursion because you have to think about like it's kind of like thinking from the end and going to the beginning on the backtracking part. I think that's why it's not natural, probably. Because usually, I think loops are more natural because usually you think like the same way that you experience time, which is just from left to right, or from the past to the future. So that's the same thing. Like on the loop is more natural because you're always going from the beginning to the end. But then on the recursion, I have to think about like on the backtracking, you start on the end and you go back. And that's the part that is confusing. Like when it reaches here, it's gonna have like the smallest from going from the left, breaking the array down from the left, and then the smallest from breaking it down to the right. Yeah, so like when the array length has like one item, I think it reaches the base case for the left, then it backtracks. When it backtracks, it gets the previous array, which was two elements, and then it calls this one with the array, I think, which is gonna break down again. But I'm not 100% sure. Yeah, I understand that this is what's like the concept, but to picture in my mind the exact way that it's happening with the recursion is still very hard. Yeah, but then let's here. So this merges them. And then it creates the other ones. It's like it creates a temporary array to merge, and then it copies them to the original one, and then deletes the temporaries, I think. Yeah. So I'm gonna move on from to the other one. Heap sort is, like I said, it's gonna be a binary tree. So it's gonna be the process of sorting the nodes on the binary tree. If I building the heap, the rip, it starts from the ends. It's starting from the middle, breaks down the middle, and then it goes to the beginning. We check to see if any children need to be swapped. There's a swap euro occurs down the tree. Chubabo. Oh, you're talking about the merge sorts? Or no? Oh, I think you're talking about this one. So if it isn't, if the root's not the largest, then it swaps the swaps the current largest with the root, and then it calls recursively. I think I understand. Yeah, I understand. It's just the confusing part is these calculations here, the I calculations. And why is the left times twice plus one, and the right times twice plus two? I think that this one, like what makes sense to my mind is that because there's always two children, so we have to do times two. We're not really sure. And this one, like why sum? That's what I don't understand. That's just how we can traverse trees that are stored in an array. Mm. That's the array. It doesn't have to be sorted. Yeah, that's what I'm trying to think about. Like the 'Cause the array, I think, is not sorted. It's just a representation of the binary tree. I wanna think a little bit more about it. Then, if I can't figure out, I just I'm gonna look at ChatGPT. But or actually, I'm probably not gonna look, because it doesn't matter that much to me. Unless I see that I need it for the stuff that I wanna do later, then I might spend. If I see that it's very useful for the stuff that I'm gonna do, then I'm gonna spend a bunch of time. But I wanna, like I said in the beginning, not sure if we're here, but like I'm trying to. I think it's always better to begin with the end in mind. So begin with the stuff that you wanna do actually, that you wanna build, and then from that point you think about what kind of algorithms are probably gonna be necessary, like the categories, and then you search the algorithms, and then you create a hierarchy because you're not gonna have time to study everything. So it makes more sense to study stuff that is actually practical, and you're gonna use. But I think that this, like, the only thing that is confusing is this part, but the rest I understand. This is just checking to see if it's bigger than the length. Pretty sure that this is the length. It's the half of the array. No, it's the length. N is the length, but it just loops over half of the array. Probably because it's a binary tree, so I think that makes sense. So yeah, I think that the reason why you do it is because it's a binary tree. So like you're only getting the N is gonna be the, like, the index is gonna be from the beginning to the middle of the thing. No, no, to the middle, uh, from uh, from the middle to the beginning. So, and you're passing the length each time. This is the middle. But why is the largest the consider the I here? It's saying largest index, I think. Because this is the index. It's not the value that is the largest. It's just the index. The reason why you start at true and is that the first non-leaf node. All leaf nodes satisfy the heap property. All the all leaf nodes satisfy the heap property. Hmm. Yeah, I think that makes sense. You're starting from the middle because of the, it's like I said before. Because, like, it has it always has children. Yeah, and that's, I'm not sure if that's a heap property. I think it is. Like, it's a binary tree, I think, property, and the heap is a subsection of a binary tree, as far as I understand now. Like, the heap is a specific configuration of a binary tree. So I think it satisfies the binary tree property, and the heap is part of that. So, you know. So like here, like let's think of in the beginning. It's gonna take the index that is at the end of the array. But that doesn't make sense, actually. It's like this would be outside of the array. So it's comparing based on the size of the array. So if the left is smaller than n. So I think that this just it checks to see if at least in the first iteration, if the elements are going to be odd or even on the tree. That's what's doing. This here is going to be -1, like divided by 2. I think that this is going to be like integer division, so it's going to round down. Then -1, and then the +1 corrects the -1 here. And that's why you have there. But the right. Yeah, so it's right and left because it's two different. I think I understand now. So this is by 1 to correct the -1 here. But it is kind of confusing though. So I think that the -1 is just because, like, for some reason, I think it's like you said, a property. I think it's a property of binary trees. But when a binary tree is stored on an array, the best way probably to loop is like you have to get from the middle because each node is going to have two children. So because of that, you have to divide by 2. But if there is an even number or even or odd, whatever one is not divisible by 2, then you have to correct that, and that's why you put the -1. But like it seems to me that this would already, like, because it's an integer division, so like maybe it is possible, maybe it's just the way that they did here, and then like you wouldn't, like you could do it like this and then just do like this instead. I think that's possible, probably, not really sure. Because I think that the +1 is just to correct the -1 here. And then it's times 2 because it's a binary tree. But I'm not 100% sure. I think largest, it means the index. So if the value of the left one is, oh, so I think that this is saying is like is comparing based on it's comparing based on the middle. It's kind of similar to binary search thing. So like this one is the last element. It's going to be the last, not the last, the middle. And this one is the last one. So compare to see if the last value is greater than the middle one. And if it is, then the largest becomes the last. Yeah, so here is the same as this one. It's checking to see if either one of them is greater than the middle one. Or whatever one is going to be on the iteration there. And if the largest is not the roots, so if either one of these happen, then it swaps the current one with the largest, which is gonna be the one that is at the end of the thing. It's not at the end, it's just I think I get it now. So like you're starting from the middle and you're walking backwards to the beginning, and then you're calling this each time. And what that's gonna do is just gonna, I think it's gonna sum to correct the iteration here. Not 100% sure why, but then it multiplies by 2 because that's the property of the heap. And when you think about a tree on an array, you have to multiply by 2 because that's the nodes, how you're gonna build the nodes or the children of the thing. So the multiplication by 2 gets the index of the child of the tree. That's what's happening, I think, because these are indexes. So I think I understand now. Like when you construct the tree, the child of the current one are gonna be 2 times on the right of the current index, and then the plus is just it's plus 1 because it's the left one, and then plus 2 because the obviously is gonna be right next to the left because they're both children of the current node. So I think I understand. So if the largest is not the current element that is being traversed, then it swaps because you want to keep the max value, I think, at the root. I'm not 100% sure though, so. But whatever. So the root is gonna be the first element. Don't understand very well though. Oh, this one's also gonna be the first one. This is also gonna be. And so I think that the heap phi puts the largest on the 0 index. And then it just calls this again. With the so, but this time this one's gonna be this size. Yeah, I don't understand very well this part. So I think what this one is doing is what I said there. It's just swapping based on, it's checking to see if it's the largest based on the values of the index. So it does that by comparing this. If it is, I think this check here is just to check to see if the index is out of bounds. So the first iteration is probably going to be, the right one is not going to be on the array. So that's why you have this. And if it does exist, then it's going to compare the values. The value of the left child, yeah, the value of the left child and the right child of the current node. Yeah, of the current, yeah, of the current node, which is the y node. So the I is the index of the current node that is trying to heap phi. So it's not the root of the tree itself, it's just the roots of the current subtree, maybe. Unless the index is of the nodes that is the root of the tree, I think. And then makes the largest equal to the index of this one. Yeah, which is the root from the child. So then compares if it is uh, if this one if the current one is bigger than the largest, then it swaps or makes it equal, and it swaps here. Yeah, recursively is so it's like it's checking based on the subtrees, based on the nodes there. So the index that passes to the heap5 function is not necessarily the one that is the root of the tree. It's just checking, it's just constructing subtrees based on the index, which is the initial array here. That's what's happening. Make sure that the child actually exists. Yeah. So, yeah. Whatever array you pass there is just gonna call recursively and just gonna organize the array based on the which one is the value, which one has the highest value. Based on that's this stuff here. So here it loops over all of them. So the thing that I don't understand very well is if I don't think that this stuff here means that the largest one is going to be the zero index necessarily. That's what I'm not really sure, but it seems like it is because of this comment here. So yeah, so it seems like this one always puts the highest value at the zero index. That would make a lot of sense. Yeah, because this one depends on the first value here. It's like it's not guaranteed that it's gonna be zero, I think. Like it's not gonna put the highest value as the zero index. I don't think that's guaranteed based on this largest. Because the I is the current one, so it's gonna be the largest. So depending on which child it is, gonna replace the largest with the value, and then it's gonna run the thing recursively here. It's gonna swap the value of I with the largest. So it swaps the value. It's kind of confusing. Oh, sorry. Oh, it does. It does, I think. Oh, so it puts the highest value as the zero index. Coming out the last loop. Run the code, maybe. I don't know. Yeah, I'm not. I don't. I'm not gonna spend a lot of time. I'm not very worried about understanding this one. I'm just trying to see if I can like make sense of it, kind of. But if I don't, then I'm just gonna move on. I don't really care about it, to be honest. So, okay, I don't wanna go through the extra efforts of actually verifying. I got this from yeah, I have the I got it from Geeks for Geeks. So it's probably correct. Uh, Based on the explanation, I don't get it very much. First, convert the array into your heap data structure using heapify, then one by one delete the root node of the max heap and replace it with the last node in the heap and then heapify the root of the heap. Delete the root node of the max heap. All the second for loop is doing is making the algo produce a min heap as well. Hmm. I'm not really sure about that. I don't think that's because it's not like the thing there is saying that is deleting, but I think this is just swapping. Like so it swaps the first element of the array with the current one, which is the last one. And then it heapifies that. I think that the thing that is difficult to understand is like to visualize what is gonna be what is the array gonna look like after you do this thing here. Because obviously the array is like a linear representation of the thing, but the thing is actually a tree. So I think that's the thing that I'm struggling. Because it's kind of hard to imagine how the index of the array are gonna translate into the way that the shape of the tree, I think. So like here is saying that the I is the root, but I don't understand that because like here is gonna be the elements of the array. Like it's gonna be the index is gonna change in the beginning. So it makes sense because it's saying that it's a subtree. So for each index is gonna like create a subtree based on this calculation here. So you consider this as the root regardless of what index it is. And then it creates the value structure based on this formula here. And then it's swapping based on this, based on the values of the related to the indexes, and then calls recursively. The recursive call is kind of confusing to understand as well. It's passing the largest as the current index. I guess it's just to check to see if the children of that one, because it is not necessarily going to be the same ones. It's not going to be the same because it's swapped. I think that's what's happening. Because it's swapping the elements, it's gonna call this again with the new, like it's the same index, but it's gonna be a new value because it's swapped. And then it's gonna check to see if the values of the child of the new value are greater or not than the current one. So I think I understand this one. If I does return a maximum max heap, yeah. Yeah, I think I understand. But what does the max heap look like on the array format? Like on the linear format? I guess that's the question. Yeah, this is the thing to understand here. I think it's going to be the consequence of this calculation here, these equations. So if it is the case that the maximum value is always going to be the zero index, then this is going to be 1 and this is going to be 2. So I think I understand now. Yeah. So the maximum value is always the 0, 1 because it, like it's an interpolation of values. But it's kind of hard to imagine, I think, to translate in your mind. So like here, like this is gonna be the eventually it's gonna be the root, and then the two next from this one is gonna be like the subroots of the direct child of the root. But then the question is like, are these ones the children of this one? I think it is, yeah. These other two are the children of this one, and then this one, the children are gonna be these other ones. I think I understand now. I get it. Well, like it has to be that because of the calculation there. So like this is the root, and then these are the childs of this one. Obviously, the values are gonna be different. So the zero index is always gonna be the highest value, so it's gonna be 13 eventually. And then it reverses at the end because he wants the sorted version. Hmm. So like it's moving the max is moving here to the end because it's the maximum value. And then it heapifies again. But the the heapifying here is kind of confusing. Because wouldn't that produce the same max heap? I guess it just heapifies the subtrees though, not the entire thing. Yeah, so is heapifying the parts. I understand now. So it's like excluding the highest value the next time that it heapifies. So it swaps the highest value with the I, and then it passes I because then it's gonna exclude the value that was the maximum. So it's like reversing the array and then heapifying the other one, and then it reverses again, like it removes again. So it does the same logic to see which one, guess the highest by heapifying, and then from the highest it swaps with the current index, and that's gonna reverse the array. As it heapifies, it goes from the right to the left, and then like creates the max heap, and then from based on the maximum value it swaps. I think I understand. Do you get that explanation or not? I'm not really sure if you know how it works, but I think I get it now. So like this one is going to be the root, which is the maximum value. Then the next two are the children of that one. Then this one, the children are going to be these ones, and then this one, the children are going to be the other ones. The children are going to follow this format here. It's always going to be multiplied by 2 based on whatever index you have right now. And then these ones are just 2 correct, I think. Nice. Yeah, so if you get it, I think I'm gonna go to the next stuff that I wanna study. But I get it now, I think. So now I'm going to spend time studying this graph coloring stuff here. And it's probably gonna take a lot more time because and the encryption stuff also is gonna take a bunch of time because it's a lot more complex, I think. It's not gonna be, it's more like a program, a software program instead of just one algorithm, so. Register spilling will be necessary for a given program. So which register should spill? We implement this algorithm, the LLVM backend comparative performance, blah, blah, blah. And it's kind of the issue here. There's a bunch of, oh, it's not that bad. There's a bunch of functions from this library here. I think LLVM stands for low level virtual machine. And is the backend of compilers. This is the part that creates or either creates the intermediate. I think it both creates the intermediate representation or the assembly version of the higher level instructions, and then converts that into machine code, I think. So it does that. It runs this algorithm to figure out what registers are gonna hold the values of the variables, I think. So the variables are stored on the symbol table, which is a consequence of the creating the lex tokens, and then the abstract syntax tree. And I think some parts of the control flow graph as well. That's you, but maybe not. You just like create a hash map or a table that stores a symbol and then what the symbol is gonna hold, I think, which are the variables. And you do that for figuring out scopes as well, I think. And then I think that this algorithm is used to assign the registers that are gonna hold the values of the program, because you can't have the same register holding two values at the same time, obviously. So, yeah. I'm not really sure which. I assume that, yeah, obviously it has to be this one because the other are header files. It's called register allocation allocator. Cogen, blah blah blah. I'm not really sure though if this is gonna be. The thing is, I from the videos I've watched, I didn't like them very much, but I didn't look for like didn't look into very in depth, and I have to look more in relationship to compilers. How does it work? So I understand more exactly like how, or maybe just look for videos related to the libraries, the LLVM. Because the problem here is gonna be understanding like all the other the stuff that it uses here because it's probably coming from the libraries. So I don't even know where to start. Maybe here's a good thing. This is a problem. This is gonna come from, and the issue of this one is that it's gonna be. I think that probably is not gonna be a very good one. Like, mm, it depends on the stuff that I wanna do. Because it is gonna be the best one to look for in the beginning because it's more closely related to the stuff that I'm trying to do now. Just create the graphs out of the compilation process. But it's not gonna be the, yeah, but I think that the other ones are gonna be hard as well. And maybe they are more like for the future, like encryption and compression. So I think I'm gonna stop here and I'm gonna go watch. I'm not really sure. I'm probably gonna watch all of the videos off stream, so it's gonna take some time, I think. So I wanna maybe fast food and transform is better to spend time before I spend time on this one. But I think this one's gonna be more related to the stuff that I wanna do. I think probably the best thing to do now is to just study a bunch of videos about all of these other ones. Then after I study all of that or watch the videos, I'm gonna need to finish reading these two different books. And then I'm gonna read again the Kenneth book and try to write down exercises. Yeah, I'm gonna try to write down exercises from these books, two books that I'm gonna read now, and from the Kenneth Rick. Then put the wraps on those books, those exercises. Then after that, I think it's probably better to just continue to try to build the stuff that I trying to build. So go back to Raylib and trying to build stuff. So I'm gonna probably have to spend a bunch of time studying Raylib source code. The functions are not very hard to understand. I follow some examples, and it looks like it's not that hard to build the GUI using Raylib and things like that. So the hardest part, I think, is going to be figuring out how to. So I have to go back to the stuff that I was doing with Python to understand how that program works and how it creates a parse tree based on a grammar, which comes from the Beckles nulls form. Just a way to write grammar for our language. So I want to get the grammar, build the deterministic finite automata, then create a graph out of that. So I think probably the stuff that is the closest to the thing that I actually want to do is this graph coloring. Maybe it would be a good idea to try to build the graph, build or implement this algorithm in the stuff that I'm trying to do there. Maybe that's the best idea. So I try to implement this one and create a graph visualization out of this register allocation. So I understand how the algorithm works and capture the graph that it creates for the register allocation and then visualize that with Raylib. I think that's probably the best idea now. So, but I have to watch all of the other videos before, I think. And the problem with this one is that like it's gonna be I have to watch a bunch of videos and then I have to understand how this library works more. This is gonna take a bunch of time, I think. There's also this other library here that I found for graphs. The graphs I'm gonna have to probably spend more time as well. Like, but the thing is, I wanna see what kind of algorithms I'm gonna need first. So this is why I said that I'm probably gonna train breadth first search and depth first search a lot more because like all this stuff that I'm thinking about doing is related to graphs. So I found this graph library here as well. So I think that they have it's boost graph. They probably have the best implementation of a bunch of different graph algorithms, but it's probably better to try to build stuff first and then because I need to have the base graph to know what kind of ways I want to display the data and get meaning out of it. And then based on that, I'm going to be able to realize what kind of algorithms are probably going to be the best. So what should I do? I'm going to see if I'm going to search for the library and install. It might be annoying as well to make it work with CMake. So I'm going to stop here and I'm going to watch a bunch of videos, all these videos, and then study this LLVM, watch videos from LLVM upstream. I think I'm not gonna watch like all the videos. I was thinking about like just typing this on YouTube and then watching all the videos that I find on the thing. But I'm probably just gonna watch one or two for each one, like to go as fast as possible, finish this as fast as possible. Then I'm going to study this LLVM library and then try to implement this. Probably the first thing to do, the best thing is try to get this graph of registers from some program and then try to visualize the graph itself. And then from that, like continue from that point. And probably gonna have to study Raylib before I do that because to understand more like how the functions work and stuff like that. So probably gonna take a long time to finish all of that stuff, and I have to read the books as well. So maybe a couple of days from now, I'll stream